All right, welcome back for the fourth lecture in the series about the non-organizable correspondence over OC.
All right, thank you very much. So last time I tried not to end early, but I failed. So this time I spent some time thinking about how I could kill some more time in this lecture. And I thought what I should do is say a little bit of something about how what I'm talking about fits with the general themes of the program at the Hausdorff Institute. So I looked up that it was supposed to be about spectral methods. And then I thought, what's that? So I looked up spectral methods on Wikipedia, and I found this. Techniques for scientific computing, writing solutions as a sum of sinusoids. So that seems, it's a tall order to connect this with what I'm talking about, but let's give it a shot. Okay, so let me recall what happened last time. So I defined what you might call a perfectoid Riemann-Hilbert functor. So the setting was R is a perfectoid ring, X is its spectrum. And I defined, or I didn't quite define, I told you about a construction which takes étale sheaves on spec R and produces objects in the derived category of R modules. And there's a little hat there to remind you that everything is always p-adically complete. So this is a construction which had a lot of nice properties. And well, there was also an upgrade of this construction. If R is a perfectoid ring, it's presented as A mod I for a perfect prism A comma I. And this RH prism bar is the reduction modulo I of a functor RH prism that goes from sheaves on X to the derived category of A modules. So eventually, I'm going to want to make use of this construction, but everything that I would say about this construction is just a more complicated version of something that I would say about this construction. So in this lecture, I'm going to focus entirely on this RH prism bar. And so the basic question that I want to ask in this lecture is, what should you do if R is not a perfectoid ring? After all, a scheme of the form spec R where R is perfectoid is not within the domain of things that people would have thought about 10 years ago, right? Perfectoid rings are essentially never Noetherian. So, what use is it to have some invariant of étale sheaves on the spectrum of an absolutely enormous ring like that? And so the answer to this question is if R is not perfectoid, if it's some much smaller ring, well, you try to map it to perfectoid rings, approximate it by perfectoid rings, and see what pops out. So motivated by that, I want to make a definition, what I'm going to call a perfected Hodge-Tate crystal. So X is this arbitrary scheme. It's always going to be assumed to be quasi-compact and separated. And here's the informal definition. So a perfected Hodge-Tate crystal is a rule. Anytime you have a perfectoid ring R and a map from spec R into X, you're supposed to assign a complex of R modules, which is p-adically complete. And that's supposed to be compatible with base change. So anytime you have a map from R to another perfectoid ring R prime, then you get a map from spec R prime into X. And the complex that you associate to that map should be obtained from the complex associated to the original map by extending scalars from R to R prime. And these isomorphisms should be compatible with composition of ring homomorphisms up to coherent homotopy, because we're working in the setting of homological algebra. We're working in some kind of derived category. So this is an informal definition. If you want to make it a formal definition, you can approach this using the language of infinity categories. There's an infinity category of perfected Hodge-Tate crystals. So I apologize. I've given this a very complicated name, just because that's what we're calling them to distinguish them from other objects which won't appear in this lecture. So to compensate for the fact that I've given them a very complicated name, I'll give them a relatively simple notation. So these will just be crystals on X, Chris X, with a little decoration here, prism bar, to remind you that we're doing a mod I version of things rather than a fancier version. And so what's the definition of this infinity category? You take the homotopy limit of the p-completed derived categories of R indexed by the category of all perfectoid rings with a map from spec R into X. And this is a homotopy limit formed in the world of infinity categories. Now, if you don't like the language of infinity categories, you could formulate this in a more classical language. The category of pairs are a perfectoid ring and a map from spec R into X forms a category, which you might call the perfect prismatic site of X. And on that category, you have an obvious presheaf of rings, which is just the thing that assigns to each datum like this, the ring R. And this category that I'm interested in, you could think of as living inside the derived category of presheaves of modules over that presheaf of rings. Okay, so what's the point of this definition? The point is that our Riemann-Hilbert construction from the previous lecture gives us lots of examples. So let's say X is any scheme and F is some étale sheaf or complex of étale sheaves. Then anytime you have a map from the spectrum of a perfectoid ring into X, you can take your sheaf F and pull it back along that map to get a sheaf on spec R, and then you can apply the construction of the previous lecture to get a complex of R modules. And one of the things that I told you was true about this construction is that it's compatible with base change, which is exactly what you would need in order to say that this construction gives you a perfected Hodge-Tate crystal. So I'm going to denote that by script RH, prism bar of F. It lives in this category of crystals. And following the principle of last time, it's in a funky font, which means that we regard it as a little bit mysterious, right? This thing in Roman font, it was just an R module, or, well, a complex of R modules. But this lives inside some category which was defined in a way that might not give you much of an idea of what it looks like. So nevertheless, we have this functor that I'm going to call the Riemann-Hilbert functor, RH prism bar. It goes from the derived category of sheaves now on any scheme to this category of Hodge-Tate crystals. And the question that I would like to ask is, can we understand it? So X is a scheme. First, we could ask, can we understand this category that I'm denoting by Chris X? What does it look like? And if you can have a sense of what the category looks like, can you understand what this functor is doing? And can you get anything useful out of this in the end? Useful invariance of étale sheaves, for example. Okay, so I first want to try to tackle the first question using what you might call spectral methods. So here's what I mean by spectral methods. If you want to understand a category C, you should try to think of C as the category of quasi-coherent sheaves on some algebra geometric object. That's what you might call giving a spectral decomposition of the category C. And that spectral decomposition is indexed by the geometry of whatever it is the quasi-coherent sheaves on. So the tautological example of this is, let's say you have a commutative ring R and you want to understand the category of R modules. Well, you can think of R modules as quasi-coherent sheaves on spec R. That's very close to just being a tautology or being a definition, but it's very useful as a point of view, right? Thinking of R modules as quasi-coherent sheaves on spec R, it suggests a lot of ideas for how you might think about things, ways that you might try to prove things that might not be obvious if you never saw the definition of the spectrum of a ring. So for example, you're saying something here like an R module is a family of vector spaces parametrized by spec R, and vector spaces are easier than modules over general rings. So an observation that a friend of mine once made to me is, mathematics, there's one thing in mathematics that we actually understand, which is linear algebra. And the rest of mathematics consists of a bunch of clever ways that people have found to reduce their problems to linear algebra. And so in this context, that funny way is to think about spec R. Okay, so this is a general thing that you could try to do if you had some category C. So let's see what happens in our situation. So let's start simple. So let's say R is a perfectoid ring to start with, and X is the spectrum of R. Well, in that case, there's not really much to say. So a perfected Hodge-Tate crystal, remember what the definition is. In this case, I would be saying every time we have a map from R into some other perfectoid ring R prime, we're supposed to give an R prime module, and it's compatible with base change. But if it's going to be compatible with base change, you don't need to specify it, except in the universal case where R and R prime are the same. So this category is just by some version of Yoneda's lemma identified with the p-completed derived category of R itself. And this identification carries this thing which is in the calligraphic font to the thing which is in the Roman font. It carries it to an invariant that hopefully we already understand something about. Okay, so let's do a case which is almost as simple. So let's let R be a commutative ring that has a perfectoidization. So there's an initial object in the category of perfectoid algebras over R. In that case, it's the same story. If you want to specify one of these perfected crystals, you just have to specify one datum, except now it's not an R module, it's an R puft module. So this category is identified with the p-completed derived category of this perfectoidization. And another way of saying that is it's identified with quasi-coherent complexes on a geometric object, which is the formal spectrum of R puft. And so now I want to generalize this. So let me introduce a construction. I'm going to call this perfectoidization, but now not of rings, but of schemes. So let X be a scheme. I'm going to define something that I'm going to call the perfectoidization of X. I'll denote it by X puft. It's going to be a functor from the category of commutative rings to the category of sets. And I'll just tell you what it is on some rings that are particularly nice. So let's say R is a commutative ring where P is nilpotent and R mod P is semi-perfect. So every element of R mod P is a pth power. And then I'll tell you what this set is. It's the set of isomorphism classes of diagrams where, first of all, you specify a map from spec R into X, but you don't just specify a map from spec R into X, you specify a factorization through the spectrum of a perfectoid ring S. And you demand that this in particular induces a ring homomorphism from S to R, and I want that to give an isomorphism from S flat to R flat. So said more informally, what I'm saying is S is an untilt of R flat, and I've specified an S valued point of X. Okay, so this is a definition. Well, I've made a definition when R mod P is semi-perfect. In general, we'll extend this to the category of all rings by demanding that it satisfies descent for the flat topology. That is, any ring has a flat cover, which is semi-perfect because you can just adjoin pth roots of its elements over and over again. And by convention, this X puft of R is going to be the empty set whenever P is not nilpotent in R. So it's a sort of p-adically completed object. Okay, so let me tell you about this construction. So X is any scheme. First, there's an obvious map from this perfectoidization of X back into X, because I told you an R-valued point of the perfectoidization is an R-valued point of X plus some additional structure. And simple example, let's suppose that you start with X being the spectrum of a perfectoid ring. Then this perfectoidization is just the formal spectrum of the same perfectoid ring. And that map up there is just the inclusion of the p-adic completion of X into X. More generally, if let's say X is any scheme, but I give you a map from spec R into X, where R is a perfectoid ring, then I can take the perfectoidization of that map, and that'll give you some map from the formal spectrum of R into this X puft. And that construction is bijective. So for any scheme X and any perfectoid ring R valued points of X are the same as R valued points of the perfectoidization, modulo the caveat that on the right-hand side, the points mean spoof R valued points rather than spec R valued points. Okay, so why am I making this definition? So let's say I give you a quasi-coherent complex on this perfectoidization. And if I have a perfectoid ring R and a map from spec R into X, I can take that complex and I can pull it back along the perfectoidization of this map. So the perfectoidization is a map from spoof R into X poofed. That pullback will give me some quasi-coherent complex on the formal spectrum of R, which I can think of as a p-complete complex of R modules. So this construction depends functorially on the ring R, and therefore it gives you an example of what I called earlier a perfected Hodge-Tate crystal. And the claim is that this construction is reversible. That is, this category of perfected Hodge-Tate crystals can be viewed as the category of quasi-coherent sheaves on this X poofed. So we have a spectral decomposition of this category of crystals, and understanding it is, in some sense, the problem of understanding what X poofed looks like. Okay, so what about that? So warning, this X poofed it's essentially never going to be a scheme, or even it's rarely going to be a formal scheme, but it's not that far off. So let's say you take any map from spec R into X, where R is perfectoid. So that induces a map from the formal spectrum of R into this perfectoidization. And this is always a representable affine morphism. And we'll say that this map from spec R into X is a perfectoid atlas if it's not just an affine morphism, it's a faithfully flat morphism. And you can always find these things. So you can always choose a perfectoid atlas, and that gives you some presentation of X perfectoid as a quotient of an affine formal scheme. So let's pick one. And then what do we learn? This X poofed is the quotient of spoof R by an equivalence relation. That equivalence relation is just the fiber product of spoof R with itself over X poofed. So let me call that E for equivalence relation. And you can say exactly what E looks like. So remember, X, I said, was always a separated scheme. So if I take the fiber product of spec R with itself over X, that's a closed subscheme of spec R tensor R. It's a scheme of the form spec S. And that S can be written as a quotient of a perfectoid ring, and therefore it, or at least after p-adic completion, it can. And therefore it's the kind of S that admits a perfectoidization. And then this equivalence relation is just the formal spectrum of what that perfectoidization is. And this gives you, I don't know, a reasonably concrete handle on what these perfected Hodge-Tate crystals are. So if once you choose an atlas, then what you're trying to understand is objects of this derived category of R that are equipped with some kind of descent data that involves this perfectoid ring S poofed. So they have some description in terms of comodules over a Hopf algebroid. Okay, so that could be useful, but let's try to extract something a little more concrete. So let R be a commutative ring. X is spec R. And now let's suppose that I give you some étale sheaf on X. It has an associated crystal. I think of that as a quasi-coherent complex on the perfectoidization. And I just want to extract a more concrete invariant by taking the global sections of this. So I could have said this without introducing the perfectoidization. So this is a complex, let's say, of abelian groups for now. And the way that you construct it is you just take all maps from R into a perfectoid ring. To each of those maps, you pull back the sheaf and apply the construction of the previous lecture. and then you take some homotopy inverse limit of all the complexes that you get this way. So I'm going to denote this by RH prism bar F, now again in Roman font, because it's a more concrete object. It's just a chain complex. And so, well, just a remark, if R was a perfectoid ring, this would be exactly the construction of the previous lecture. And a question that you can ask is, how much information do we lose when we take these global sections? And the answer depends on what you consider the right-hand side to be. So again, R be any commutative ring. There's this natural map from the perfectoidization to R. And therefore, when I take this inverse limit construction I mentioned on the previous slide, it's always going to have an R module structure. That is, you can think of RH prism bar as in the previous lecture as a functor from étale sheaves to the category of R modules. But sometimes you could do better, right? If R has a perfectoidization, then actually we know exactly what this perfectoidization is. And therefore, this functor doesn't just have a structure of a module over R, it has the structure of a module over the perfectoidization. So let's try to amplify this observation. Let's go back and look at this perfectoidization construction from the previous lecture, or perfectoidization definition. So in the previous lecture, I told you a perfectoidization is an initial object in the category of perfectoid R algebras, but I also warned you that these don't usually exist. But here's something that you could always do. You could take any ring R that you like and take the global sections of the structure sheaf on the perfectoidization of spec R. And a more concrete description of that, you just take all perfectoid R algebras and take their homotopy inverse limit regarded as a chain complex. So now, if R has a perfectoidization in the sense of last time, then there's an initial object in the category of perfectoid R algebras, and you only need to take the subcategory consisting of that one object to compute the inverse limit. In other words, this definition agrees with the previous definition. And in that case, that inverse limit, I said homotopy inverse limit, but it would just be a complex concentrated in degree 0. It would be a commutative ring. But in general, what you get out of this construction is a chain complex rather than a commutative ring. And if we want to use it as a replacement for the perfectoidization, well, I want to think about this in terms of spectral methods. And now what I mean by that is I want to use the same kind of ideas that people in algebraic topology use when they want to do algebra in the stable homotopy category, in the category of spectra. So it's sensible to do commutative algebra to talk about things like commutative rings, modules, and so forth in a setting of something like the derived category of R modules. And well, in order to get a good theory, you really want to work in that derived category in a homotopy coherent way. For example, viewing D of R as an infinity category and thinking about commutative algebras and modules formulated using that language. So in this setting, this R puft, it's something that naturally lives in the derived category of R modules, but it has a commutative algebra structure in that world. So it's an example of what's called an E infinity algebra over R. And it makes sense to talk about modules over this E infinity algebra. And these form an infinity category that I'm going to write as D of R puft. It's some kind of version of the derived category, but now not for an ordinary commutative ring. And it has a subcategory of P complete objects that I'm going to indicate by putting a hat over it. And well, what's an example of a module over R puft? Well, anything that comes out of this Riemann-Hilbert construction, right? This R puft was defined as the inverse limit of all perfectoid R algebras And this RH prism bar of F is defined as the inverse limit of a system of modules over that system of algebras. And therefore, you could promote this RH prism bar to a functor from sheaves on X to this p-complete derived category of the perfectoidization. So let me say a few words about what this perfectoidization construction looks like. So a priori, it was defined as some enormous inverse limit, and it might not seem like something that you can necessarily get a very good handle on. But in the situation where R is an algebra over a perfectoid ring, there's a very nice description of this due to Bott and Schulze. They showed that this perfectoidization can be computed using the formalism of prismatic cohomology. That is, there's some chain complex, which is the prismatic complex of R, and it's equipped with some Frobenius map. And if you invert the Frobenius map and appropriately complete, then you get something which, after mod I reduction, is this now a chain complex, which is this perfectoidization. So I mentioned a version of this last time, which is the case where R was actually a finite algebra over a perfectoid ring A mod I. And in that case, they proved that these objects are actually just chain complexes concentrated in degree 0. But you can consider these chain complexes in general, and they recover, first of all, the thing described by the previous construction, but because they can be described in this way, essentially by taking some object that you might understand well already and inverting some Frobenius map, you get a lot of control over what this R perfectoid looks like. And that actually translates into a lot of control over this perfectoidization construction at the level of schemes. So let me say what I mean by that. So let R be a commutative ring, and I'm going to assume that it's an algebra over a perfectoid ring. And the heuristic I want to explain is that this perfectoidization of the spectrum of R, it's like the formal spectrum of R puffed. So what do I mean by that? Well, one case is when R puffed meant what it meant in the previous lecture. Like suppose there was an initial object in the category of perfectoid R algebras, then this is something which is literally true in the category of formal schemes. Both sides are p-adic formal schemes, and they're isomorphic to each other. But this feels like it's true more generally in the following sense. So let's S be a commutative ring in which P is nilpotent, and suppose you want to compute the S valued points of X puffed. So this I described for you earlier, that's some set. And that set can be computed as Homs from R puffed into S, but now those Homs are computed in the world of E-infinity algebras. And in particular, the right-hand side is something that a priori you might expect to see a mapping space in the world of E-infinity algebras. But I'm claiming as part of this proposition that that's actually a discrete space. So that's a sense in which this X puffed, it's like the formal spectrum of something, but that something isn't a ring in the usual sense. It's one of these E-infinity algebras. Now, having an affine scheme is particularly convenient if you want to understand quasi-coherent sheaves, because you're just talking about modules over whatever the coordinate ring is. And something similar happens in this setting too. So now let me assume not just that R is defined over a perfectoid ring, but that it's finitely generated over a perfectoid ring. And in that case, I claim that this global sections functor, which takes these perfected Hodge-Tate crystals, remember, those are the same things as quasi-coherent complexes on this perfectoidization. You don't lose any information by taking global sections. The global sections functor is an equivalence of infinity categories. You don't lose any information, provided that you remember that the right target of that functor is not modules over R, it's modules over this perfectoidization. So if you don't have to think about this calligraphic RH, you can just think about this Roman RH, but you have to remember a module structure, which is well, something to be a little careful of, because this is now a non-connective E-infinity algebra. And let me remark, the finite generation is not something you can completely eliminate here, but if R is just defined over an E-infinity algebra, these two categories are still closely related to each other. The left-hand side can always be viewed as a sort of completion of the right-hand side. Okay, so we have this Riemann-Hilbert functor, and it's important to remember its upgrade to something that produces modules over the perfectoidization. And let me just summarize some of its properties. And these should all look exactly like properties that we mentioned in the last two lectures. So first, if you evaluate this on the constant sheaf, you get, well, not R, but the perfectoidization of R, which is now a complex. It takes tensor products of sheaves to tensor products of complexes, with the caveat that everything is happening in the derived category, and the tensor product is relative to this perfectoidization. And it's also compatible with base change. So if S is an R algebra, which is also finitely presented over a perfectoid ring, for example, if it's finitely generated over R, then if you wanted to, you could take a complex of sheaves on R, pull it back to spec S, apply the Riemann-Hilbert functor there. It's obtained from the Riemann-Hilbert functor applied to the original complex by some extension of scalars procedures. And again, the only caveat is that it involves these perfectoidizations. And it's also compatible with direct images along finite morphisms, for example, closed immersions. So these are all relatively formal properties that this Riemann-Hilbert functor has. But I would like to spend the rest of the lecture talking about non-formal properties. And the first question that I want to ask is, does this RH prism bar have any good finiteness properties? So let's start by thinking about a case that we should understand well, which is when we're in characteristic P. So the simplest perfectoid rings are perfect fields of characteristic P. And let's suppose that R is a finitely generated algebra over such a field, right? X for its spectrum. And in that case, you could take an étale sheaf on X, apply this construction, and well, we have essentially the formula that I gave you for this last time, which is to apply the construction of lecture 2 to the complex of sheaves of FP vector spaces that you get by reducing F mod P. So an example, you could take R to be a polynomial ring in one generator, and you apply this construction to the constant sheaf, and what you'll produce is the perfection of that polynomial ring in one generator. And that doesn't look finitely generated as an R module. But this is misleading. In mixed characteristic, the situation is actually much better. So I want to consider now the next simplest kind of perfectoid ring, which is a perfectoid valuation ring. And I'm going to assume that P is not equal to 0 in OC. And so the fraction field that you get by taking OC and inverting P is a perfectoid field of characteristic 0. Or that's just a definition of what it means to be a perfectoid field of characteristic 0. So let R be a finitely generated algebra over OC. And let me write R hat for its p-adic completion in the following discussion. And well, something to be careful of is that a valuation ring like this is essentially never Noetherian. The maximal ideal, for example, is not finitely generated. So these are very far from being discrete valuation rings. And as a consequence, these rings like R hat are essentially never Noetherian. And the theory of finitely generated modules over rings like R hat is not well behaved. Finite generation is not necessarily the kind of thing that you want to look at. But there's a replacement for finite generation in this context, which is uses the sort of almost commutative ring theory. So let M be an R hat module. And recall what it means for M to be finitely generated, that if there exists a surjection from R hat to the N into M. So here's a weaker condition. M is almost finitely generated if you can't necessarily find a surjection from R, sorry, that should be an R hat, from R hat to the N into M, but you can find a map which is as close to surjective as you want, meaning that you can get the co-kernel of that map to be annihilated by arbitrary elements belonging to the radical of P inside of OC. So let me give you an example. So let's say OC is a ring in which you can take any roots of P that you like. So then you could take a direct sum over all positive integers n of R hat reduced modulo P to the 1 over n. So that's not a finitely generated module, but if you just take the first 1,000 pieces of this and add them up, they give you a finitely generated submodule. And if you mod out by that, everything is annihilated by P to the 1 over 1,000. So that's what you have to check in order to know that this is almost finitely generated. And now, proposition, this ring R hat is almost Noetherian in the sense that every ideal in R hat is almost finitely generated. So I learned this recently from the thesis of Bogdan Zavyalov. And I was surprised that I didn't see this in Gaber and Romero. But he said that the argument is essentially due to Kiel in a different language. So a consequence of this is that when you're working over rings like this R hat, sorry? I looked at the wrong one. Okay. Okay, so this guarantees that when you're working over rings like this R hat, this theory of almost finitely generated modules will work very well. And that's a good finiteness condition to impose. And that finiteness condition is satisfied for the sheaves that we're interested in. So let's take some constructible complex of sheaves on X. And the theorem of Zavyalov is that if you apply this Riemann-Hilbert construction, you produce a complex of R modules, and all the cohomology of that complex are almost finitely generated in the sense of the previous definition. So a little while ago, this finite generation looked really bad because sheaves coming from the special fiber looked like they were contributing a lot of modules, which didn't look finitely generated at all. But anything that comes via this Riemann-Hilbert correspondence from a sheaf on the special fiber of spec R, from spec of R mod P, is actually almost zero. And any almost zero module counts as almost finitely generated. So as long as you work in the almost category, this construction has very good finiteness properties. And this was really the starting point for this. So I'm telling the story out of order. So Bogdan proved this theorem, and Vargov found out about it. And then Vargov observed that you could take the thing that he was proving the theorem about, which was happening in the almost category, and amalgamate it with the Riemann-Hilbert construction that we had done in characteristic P. And that's sort of how we arrived at the construction of these objects. So let me tell you a little bit about this finiteness theorem from the point of view, from the more original point of view. So first, I want to globalize these constructions. So I've been talking about sheaves on an affine scheme, but let's say X is any scheme which is a finite type over a perfectoid ring. And let me write X in a Fraktur font for the p-adic completion, the p-adic formal scheme. And well, you can globalize the construction that I described to produce a functor from étale sheaves on the scheme X to the quasi-coherent derived category of the formal scheme. And so this construction is essentially determined by the requirement that when X is affine, it's the construction we were already talking about. Namely, we apply RH prism, we view that as an R module, and then we just take the associated quasi-coherent sheaf, and it's local on X. It's compatible with Zariski localization. And just a warning that this carries the constant sheaf on X not to the structure sheaf of this formal scheme, but to what you might call the perfectoidization of the structure sheaf, a complex which is not in a single degree. Okay, so I'm going to be interested in some things that are pretty close to algebraic geometry. So let's be in the situation where X is a scheme of finite type over OC. I'm going to write X-eta for its generic fiber. I'm going to write Fracture X for the formal completion of X. And I'm going to write calligraphic X for the generic fiber of that formal completion. That's a rigid space over C, or an adic space. And as in the previous lecture, I'm going to write OX plus for the sheaf of integral functions on that adic space. And now the picture that you're supposed to have here is that there's some commutative diagram where X is being glued from two pieces. So there's this open subscheme, X-eta, which is the locus where P does not vanish. And then there's this formal subscheme, Fracture X, which is the locus where P is very small. And then there's this calligraphic X, which lives in a different world, which is the intersection. It's the locus where P is very small, but somehow it still doesn't vanish. So let me make that a little bit more precise. Every arrow in that diagram actually has a map associated to it, a map of étal sites. So there's a diagram of étal sites here. It doesn't commute. It commutes up to a non-invertible natural transformation. And the data of that natural transformation is encoding the sense in which X is glued from these two pieces. So the details of this are not important. I just want to talk about these maps mu and nu. So this map nu is sometimes called the p-adic nearby cycles functor, at least if C is an algebraically closed field. And the reason that I'm telling you this is that in the almost category, this Riemann-Hilbert construction that I was describing to you earlier has a formula in terms of this diagram. Namely, if you want to compute, say you take a sheaf that lives on the generic fiber, so you could extend it by 0 to get a sheaf on X and apply this Riemann-Hilbert construction. In the almost category, that is computed in the following way. You take your sheaf, you pull it back to this rigid space, you tensor it with this sheaf OX plus, and then you push it down to the formal scheme along this nearby cycles map. And so the proof of this, well, I said something like this at the end last time. And the thing that I said at the end last time more or less formally implies this. When you input the fact that locally for the pro-étal topology, the things like X, classical rigid spaces, can be made into perfectoid spaces. Okay, so in this language, let me state the theorem the way Zavyalov would have stated it. So let X be a formal scheme of finite type over OC. And let me write calligraphic X for its adic generic fiber. And there's a good notion of constructible for p-adic étal sheaves, or on something like this rigid space X due to Bargov-Bott and David Hansen. And if F is constructible, you can take F, you can tensor it with OX plus, and you can push it down along this nearby cycles map to get a sheaf on the formal scheme. And his theorem is that's an almost coherent sheaf. It's in terms of on local affines, it's described by modules which are almost finitely generated. All right, so let me. What kind of constructibility? So it's true more generally if something is just. Sorry, what you're asking? What's their definition in the rigid case, or you're worried about?
Yeah, I'm worried about openness.
So constructible means there's a Zariski stratification of the rigid space such that it's locally constant on each stratum. Yeah. Okay, so let me describe a consequence of this. How am I doing on time? Oh, plenty of time. Okay, so here's a non-trivial consequence of this. So now let's say I give you a proper morphism of schemes, and they're a finite type over a perfectoid ring, so that this RH prism is well defined. So then there's a diagram that you could write down. You can look at étale sheaves on X, étale sheaves on Y. Those are related by some kind of direct image functor. And you can also look at quasi-coherent sheaves on their formal completions, X and Y. And those are related by some kind of direct image functor in the world of quasi-coherent sheaves. And the claim is that this Riemann-Hilbert construction intertwines those direct image constructions, provided that F is a proper morphism. So this is a version of the primitive comparison theorem of Peter Schulze. So let's see a little more closely what this is saying. So you have a complex of sheaves on the space X upstairs. Then you can take its direct image in the world of étale sheaves to get a complex of sheaves on Y, and apply the Riemann-Hilbert construction on Y to get a quasi-coherent complex on its formal completion. Or you could do those constructions in the other order. And there's a natural comparison map that you can write down, for example, without knowing that F is proper. Now, if F is a proper and smooth morphism, and F is a local system, this is essentially what Peter studied. And he showed that this map is an isomorphism. And the essence of what you needed to show there is that you had some reasonable finiteness for the kind of things that are given by this p-adic nearby cycles construction. But Bogdan has proved this in more generality, and you can remove some of the niceness assumptions on the both on the morphism. You don't have to assume that it's smooth, and on the sheaf, you don't have to assume that it's local system. Now, in both of these cases, the argument involves really the p-adic nearby cycles construction, which is computing what the Riemann-Hilbert functor looks like in the almost category. So the statement that I made on the previous slide is something a little bit stronger. It's saying that it's actually an isomorphism, not just an almost isomorphism. And that's essentially because you can see what's going on at the level of the special fibers by comparing with the Riemann-Hilbert functor that we discussed in lecture 2. So lecture 2 ended a little bit early, but if I had known that I needed more material, I might have discussed how that Riemann-Hilbert correspondence behaved with respect to proper direct images. And the upshot would have been it behaves well with respect to proper direct images. And this is the consequence for us today. Okay, so let me say a little bit more about this Riemann-Hilbert functor on the theme of non-formal properties that it has. Let's study its exactness properties. So let's simplify a little bit. So let X be an OC scheme. I'm going to assume that it's flat, also a finite type. And I'm going to write X0 for its special fiber in the non-reduced sense. I'm just going to take its structure sheaf and mod out by P. And I want to study this Riemann-Hilbert functor as I just want to study what it does on P torsion étale sheaves that are extended by 0 from the generic fiber. So RH tilde J lower shriek goes from FP étale sheaves on this generic fiber. And if we're inputting sheaves that are P torsion, we're going to output quasi-coherent sheaves that are P torsion. In other words, we're going to get sheaves that are supported on this special fiber X0. So that's a construction, just a special case of the construction given earlier. And what can you say about it? Well, first statement is that it's left T exact if I give both these categories their standard T structure. And the proof of that is something which is essentially formal, right? So left exact is saying something like it takes co-connective objects to co-connective objects. And now this Riemann-Hilbert functor locally was computed by taking an inverse limit over all perfectoid algebras of a Riemann-Hilbert functor that we studied last time. And last time I told you that that Riemann-Hilbert functor had some exactness properties. And co-connective objects are stable under the formation of really big inverse limits. And this is a consequence that pops out. But it's not an exact functor. It's it's very far from being right exact, because one of the properties that this has, well, I told you that if you took the constant abelian sheaf on X and applied this construction, you were supposed to get the perfectoidization of the structure sheaf of the formal scheme. So here we're applying this sheaf, this construction to FP étale sheaves. So instead we'll get the perfectoidization reduced mod P. And that is typically something that has cohomology in many degrees. Its cohomology is interesting. We're going to talk about that next week. So this is very far from being a right exact functor if you give both sides the standard T structure. But even though this complex has cohomology in a lot of degrees, it doesn't have cohomology in too many degrees. The number of degrees is bounded by the dimension, the relative dimension of X over OC. And a consequence of this is that this, or maybe an amplification of that statement, is that this functor is right T exact if you give the left-hand side the perverse T structure instead of the standard T structure. In other words, it's a functor which carries perverse sheaves on the generic fiber to connective complexes on X0. So that's another thing. Once you know that this construction has some good finiteness properties, you can ask how it interacts with duality. So let's be in the same setting as the previous slide. Let me think about Riemann-Hilbert just as going from p-torsion étale sheaves on the generic fiber to quasi-coherent sheaves on X0. But let me actually not look at quasi-coherent sheaves on X0. Let me take its almost category. Let me mod out by complexes that are almost zero. By modding out by complexes that are almost zero, we expect this, this functor to have satisfy good finiteness conditions. And the theorem, first of all, there is a good theory of Grothendieck duality for in the almost category for these almost coherent sheaves on something like X0. There's a theory of Grothendieck duality here, and this Riemann-Hilbert functor, it exchanges Verdier duality in the world of étale sheaves with Grothendieck duality in the world of almost coherent sheaves. And in combination with the previous slide, this has a non-obvious consequence. So in the previous slide, I told you this functor was right T exact if you give this side the perverse T structure and this side the standard T structure. Now the perverse T structure is self-dual under Verdier duality, but the standard T structure is not self-dual under Grothendieck duality. So if you combine these two statements, if you use this statement here to dualize the statement on the previous slide, you're going to get a new statement. And that new statement says something like this. It carries complexes of étale sheaves that are perverse co-connective to complexes of coherent sheaves that are perverse co-connective. It's saying something about how bounds on local cohomology on the left-hand side can also give you bounds on local cohomology on the right-hand side. Okay, so let me just close by describing a fantastic application that Bhargav found for all of this. So Bhargav's, I think one of his big motivations for wanting to think about this was to prove a particular theorem. So let R be an integral domain and let K be its fraction field. And then you can look at the integral closure of R inside an algebraic closure of K. So I'll denote this by R plus. And Bhargav recently proved that if R is an excellent domain, then R plus mod P is Cohen-Macaulay. So it requires a little bit of explanation of what that means, because a ring like R plus is very far from being Noetherian, and R plus mod P similarly is not Noetherian. But essentially, even though a ring like R plus is not Noetherian, its spectrum has finite Krull dimension. And you can make sense of what it means to be Cohen-Macaulay by demanding some vanishing of local cohomology. And well, the proof of this has many ingredients, and not all of them are before us. but let me just indicate a little bit of what goes into it. So a special case would be if R is the kind of commutative ring we were just talking about, something which was a finite type over OC. And in that case, you can look at the map. Let me take this ring R plus, look at its spectrum. Let me call that X plus. And so that's some scheme that maps to spec R via a map which is not finite, but it's profinite. It's an inverse limit of a system of finite maps. And now this ring R plus, it becomes perfectoid when you p-adically complete it. And this map pi is kind of like a finite map, so it should be compatible with the Riemann-Hilbert construction. And in the Riemann-Hilbert construction, if you're over a perfectoid ring, it does something very concrete. It just takes the constant sheaf back to the ring that you're interested in. That's if you took the constant sheaf with the value z. So if you apply it to the constant sheaf with value fp, you'll get this ring R plus mod p that you want to study. And now, because of this statement that I told you on the previous slide, this sort of non-obvious t-exactness property of the Riemann-Hilbert construction, you get information about the local cohomology of R plus mod p if you can understand the local cohomology of this étale sheaf, the constant sheaf fp on this scheme X plus. And then the upshot is this is something you can understand very well. So this ring R plus is absolutely integrally closed, and that forces the étale topology of the scheme X plus to be very simple. So for example, there's no difference between the étale topology and the Zariski topology for such a scheme. So these are some of the ingredients that Bhargav used in obtaining a very non-trivial consequence in commutative algebra. All right, I think that I will stop there. Thank you very much.